Alrighty, guys. Good morning. I hope you can all hear me nice and clearly. Unfortunately, we do have some folks doing some work outside the house. The company that's renting us this house was a little late on like blowing off the roof and fixing the fence and doing all those little things. So that's going on behind me. I'm going to do my best to speak loudly and clearly so you can still hear me despite that. If you do have any problems hearing me, just like, you know, hold down spacebar or whatever, shout out, be like, hey, I can't hear you, and I'll know to speak a little more loudly. Let's go ahead and flip over to the doc cam and we can get started because we do have a bunch of cool stuff to talk about today. Oh, that's right, gotta do this. Come on. Come on. Not working? Oh, yeah. Okay. Connect. There it is. All right. Yeah. Okay. So this is MAC2311, section 002. Today is a lecture, and the date is the 15th. So I hope you guys enjoyed your weekend off. I know a handful of folks had some work to catch up on, and I got a bunch of extension requests. I granted all of those last week, so I'm really proud of those of you who worked hard over the weekend, even though you didn't have anything fresh. And to anybody who didn't have any work to do for this class, I hope you enjoyed the holiday in whatever way you like to enjoy those things. Today, we're going to formally talk about implicit differentiation. This is section 3.5. And we might introduce related rates, which I think is actually section 3.9. The textbook jumps around a little bit here. There are some sections that we're not going to cover. 3.6 is derivatives of log functions. Yeah, we are going to cover that. But then we're going to jump to 3.9. So I'll put it like this. So we're going to do implicit differentiation and derivatives of logs. That's 3.6, that's 3.6. And then we're going to introduce related rates given enough time. And really the plan for this week is to finish related rates. I'd like to get this done. Then if possible, where are we here? I'd like to get to 4.1 also, which is on, 3.10 and 4.1. 3.10 will probably be the last thing we do this week. 4.1 will probably have to wait till next week. So this week we're going to do 3.5, 3.6, 3.9, and some 3.10. So we got quite a bit to cover. Implicit differentiation we talked about last week. We talked about this last Friday. We gave a kind of gentle introduction to implicit differentiation. We talked about why we would want to do it and the theorems that underlie it. Today, I'm going to focus purely on the mechanics of implicit differentiation. Just how do you go get shit done? Not so much of the like what theorems are running in the background or why do we think we can do this. We're going to assume that we can calculate the things we want to calculate. We won't be worrying about whether they exist or not, like we did on Friday. And we're just going to dive right in and do it. What else should I say? Oh, there will be a new homework. Just to make sure everybody's clear on what's going on. Homework 6 will open today. And will be due next Monday. And your exam 1 grades. Those will be out by Wednesday. I'm shooting to have them done by the start of class on Wednesday, but it's possible that I'll need that afternoon to finish them up. It depends on how other things go. Are there any other announcement-y things? Can't think of anything off the top of my head. So let's get started. All right. So this is section 3.5 on implicit differentiation. And what we're really doing here is we assume y is a function of x. And then we can use the chain rule to differentiate what are called implicit expressions involving x and y. Or any independent / dependent variable pair. Right, so normally we assume that normally when we're working with this stuff, we think of x as the variable and y as the output variable. So like x is the input or independent variable and y is the output or dependent variable. But sometimes it's like t and s or something, right? Sometimes we use different symbols. So the rules that we're going to use here work just as well for any other set of variables. And since we've seen a little bit of this already, I wouldn't mind just beginning with some examples. So yeah, we can start here. This is something that we did last time. I can ask us to find a formula for dy dx from the circle, from the x squared plus y squared equals whatever. I think we did the unit circle last time. The idea here is that using implicit differentiation and the chain rule, we can jump in and differentiate on both sides of this expression. I can apply the operator ddx to both sides of this expression and then try to solve what I get for dy dx. Now, we'll write y prime for dy dx a lot here because y prime is just a little easier to write. So you'll see me using this notation a lot today. I've got nothing against the Leibniz notation. If you want to write dy dx instead of y prime, that's fine, but I prefer the y prime. The idea is that we apply the operator ddx to both sides. The challenge is that this has x's and y's in it. You could try solving this for y first. That is possible here. Sometimes it's not possible. In this case, it is possible to solve for y. But that expression is harder to differentiate. So we're just going to jump in here and apply ddx to both sides. If I do that, the derivative ddx of x squared is 2x plus the derivative of y squared is 2y times the derivative of the inner function. Remember, y, we're assuming here, is a function of x, right? In other words, this is like an outer and an inner function. The outer function is the squaring function, and the inner function is y. So when we differentiate the outer, leaving the inner alone, we get 2y to the 1, and then I need to multiply by the derivative of the inside. Well, that is y prime. So that's 2y to the 1, make clear that that's a 1, not a prime, times y prime. And on the right-hand side, I have ddx of 1. Well, ddx of 1 is 0. I think I didn't write this 1 at first. Make sure you go back and add this 1. So the hard part is differentiating the y stuff, right? Realizing that y squared isn't just going to become 2y, it's going to be 2y, y prime. And kind of the thing that, like, if you're wondering, like, how can I think about this in my head and make it work out? What do I need to do? Just anytime you differentiate a piece that has a y in it, you have to multiply by y prime. That's really all that's going on mechanically. You can. So Mackenzie asks a really good question. Why aren't we using the chain rule on the x piece? So let me dive into this a little bit. This is a good question. Answer is we are, or we don't need to, however you want to say it. I would say we are. If you apply d dx to x squared, you can think of that as 2x times x primed. But what is x primed? What is the derivative of x? It's just 1. This is 2x times 1, or just 2x. This is the big difference between an independent variable and a dependent variable, right? X is the independent variable, and I'm differentiating with respect to x. That's what the dx in the bottom of the d dx notation means. It means take the derivative of this thing, take the derivative of the thing next to me with respect to the variable x. In other words, treating the variable x as the independent variable. Y is a function of x. Y is the dependent variable, but x is not really a function of x, it's independent. If you want to think of it as a function of x, you can, but then x primed is just 1. The derivative of x on its own is just 1. So even when you slap on the x primed, even if you try to attack this piece with the chain rule, the thing that you would multiply by here is 1, and it would always be 1. So if you want to, you can think of this piece as coming from the chain rule and having a little x primed here. And if we were differentiating with respect to some other variable, if we were differentiating with respect to like the variable t, that would be really important. But here we're differentiating with respect to the variable x, and this is an expression just involving x. So when we slap on that x primed, if you want to think about it that way, x primed is just 1, it doesn't change anything. This is kind of related to another very good question about the chain rule from last week. When do we stop with the chain rule? When do I know I've gone like all the way into the inside? And the answer is, well, when your inner derivative is 1, right? When you're not getting anything new out of digging a layer deeper. Does that help, Mackenzie?
Yes.
Okay, cool. So here we get this expression, which we can then solve for y prime. So I'll just write this a little bit less awkwardly. This is 2x plus 2y y prime equals 0. Now I can subtract the 2x over and I get 2y times y prime equals negative 2x. And then I can divide over the 2y, and I get y prime equals negative 2x over positive 2y. The 2's cancel. I get negative x over, negative x over y. Yeah, the 2's cancel, sorry. And that's it. This is your expression for y prime, or dy dx. It has both variables, x and y in it. It doesn't just have x in it. So if you wanted to use this to find a tangent line like we did in our last class, you would have to plug in both the x and the y value at the point of tangency to get the slope out. Okay. Are there any questions about how we got this expression for y primed? So the y prime came from the chain rule at this step, Fabrice. When I differentiate x squared, it becomes 2x. When I differentiate y squared, because y is not the independent variable, I get 2y to the 1, that's differentiating the outer function, the squaring function, and then I have to multiply by the derivative of the inside function. The inside function here is just y, so the derivative of the inside function that I have to multiply by according to the chain rule is y prime. So when I differentiate the y squared, I get 2y times y prime, and that's the chain rule. Another way you can think of this is to write it down, right? So y is d dx of y squared equal to 2y y prime. Well, y is a function of x. We could write y equals g of x. So d dx of y squared is really d dx of g of x all squared. And now if we differentiated this thing using the chain rule, I think we all agree we would get 2 times g of x to the 1. All right, the 1 here is a nice obvious 1, times g primed of x, right? That's how the chain rule would work here. So that's 2y times y primed. So it really is just the chain rule. There's really nothing special going on here. The only sort of underlying weird assumption is that y is a function of x. But that's the assumption that we're always making, right? That's the assumption that you've constantly made throughout your algebra classes, that y is equal to f of x for some function f. So when you differentiate something like y squared with respect to the variable x, we're taking the derivative with the assumption that x is the variable. We differentiate the outer function, that gives us the 2y, and then we multiply by the derivative of the inner function, that gives us the y primed. And you can maybe see it a little bit more clearly looking like the chain rule here, right? Where you differentiate the square of the function g of x. To do that, you differentiate the outer function. That's like differentiating the squaring function, yeah. The 2 comes down, the power reduces by 1. But then by the chain rule, since this inside is some function, you have to multiply by the derivative of the inside. Well, if y is g of x, then this is the same thing as 2y times y prime. I certainly don't want to have to write all of this every time, so we want to get comfy just working directly here. The reason the derivative of y is not 1 is because we're not differentiating with respect to the variable y. If this operator were d dy, then the derivative of y would just be 1. But we're taking the derivative with respect to x. Right, the variable here is x. So again, I point you down to this thing. Think of it like this. It's the chain rule. If y is g of x, then d dx of y squared is d dx of g of x all squared. If we differentiate this expression using the chain rule, do you see how we get this expression out? This is a straight up chain rule thing. We differentiate the outer function, that's the 2, the squaring function here. 2 comes down, power goes down by 1, we leave the inside alone, and then we multiply by the derivative of the inside. Well, if y is equal to g of x, then g primed of x is y primed. So it all depends on what you're considering the independent variable to be, Holly. Here, the independent variable is x. We're differentiating with respect to the variable x. That's why this notation is important, the d dx. It tells you what your independent variable is. So this thing differentiates like normal, but this thing differentiates using the chain rule. Okay, cool. I know this stuff is a little bit hard to wrap your head around, and it's kind of one of those things that you sort of get used to and then understand. Like learning the subjunctive tense in a new language or some weird shit like that. You kind of learn the mechanics, you do it a little bit, and then you'll be like, oh, yeah, I get that, but it's going to come a little bit down the road. So remember, when you bump into any piece that isn't your independent variable, differentiate with the chain rule. Just multiply by the derivative of the inner function. You'll never hurt yourself by doing that. If you happen to do that with the independent variable, you'll just have an x primed here and you go, oh, d dx, x prime, that's 1. All right. So that was an example we looked at last week. I'd like to look at something a little bit harder and a little bit newer next, something we haven't seen yet. Let me see what the textbook has. They got some good stuff in here. That's kind of a little much. Yeah, here they differentiate 2 ways. We don't want to fuck with that. That's okay. Something involving some trigonometry would be nice. Yeah, sine of x plus y equals y squared cos x. What do we have there? Y squared times cos x. Okay. So I'm going to apply the differential operator d dx to both sides. On the left-hand side, I'll have d dx of the sine of x plus y. And on the right-hand side, I'll have d dx of y squared times cos x. And I'll differentiate following whatever rules I need to on both sides. The left-hand side is going to require some chain rule for sure, because I've got the sine on the outside, and then I've got this x plus y on the inside. The right-hand side is going to require some product rule, right? Because I've got some multiplication going on over here. So let's do the right-hand side first. If I follow my product rule, I'll just write it all out. This is d dx of y squared times cos x plus y squared times d dx of cos x. That's the product rule.
Would that mean we had to do the chain rule inside the product rule with the y squared?
Yep, we are going to use a chain rule here. Yep, and that's kind of why I'm writing it out schematically like this before we dive in, so that we can take our time and focus on this. So yeah, good observation. We will need the chain rule here. Before I dive into that, I want to also kind of write out schematically what we get on the left, or see what we have. So here, if I differentiate the outer function, leaving the inner alone, the derivative of sine is cosine. So I'll have cos of x plus y. But then by the chain rule, I need to multiply by the derivative of the inside, which is d dx of x plus y. So this is where we end up. And now we have to compute all the little derivatives. I'll start over here, since this is the piece that Mackenzie made that observation about. The derivative d dx of y squared, again, I have to think of y as a function of x, so I know I'm going to need the chain rule. If I differentiate the outer, I get 2y. And then by the chain rule, I have to multiply by the derivative of the inner. So I get 2y times y prime. Or if you wanted to write dy dx instead of the y prime, that would be fine also. Then I also have my cos x term here, right? This is multiplying cos x. And then over here I have y squared times the derivative of cos x, which is negative sine of x. And you really should put this in parentheses so it doesn't look like they're subtracting. You can tell that they're multiplying. On the left-hand side, I have cos of x plus y times, and now this is outside the cosine function, the derivative of x is 1, plus the derivative of y is 1 times y prime. All right, so this is kind of a neat follow-up to what Holly was saying a second ago. Here, the derivative of y, why isn't that just 1? What does it come out to? Well, the derivative of y, the derivative of the outer function there is 1, but then we multiply by the derivative of the inner. So it's 1 times y prime. We just get y prime. So this is what's called an implicit expression in y prime. I need to solve it for y prime. I'm going to try to solve this for y prime now, and that will give me the derivative I want. Can anybody give me some advice? How could I begin solving for y prime in this expression? We've got a y prime here, we've got a y prime here. I'm not sure what the star indicates there, Mackenzie. What do we mean by y? Oh, like y times y prime?
I mean y plus y prime on the derivative of x plus y.
Well, the derivative of x is definitely just 1, right?
Yeah.
So this piece is a 1, and then this plus is going to come along, and then the derivative of y itself is just y prime. The derivative of the outer function here is 1. Right? You differentiate like normal, so just like x would differentiate to 1, this would differentiate to 1. But then you have to multiply by the derivative of the inside. So this is going to be 1 times y prime rather than y times y prime. Does that make sense?
Yes.
Couldn't you divide both sides by cosine x plus y to isolate the 1 plus y prime on the left side?
That's true, but I also have a y prime on the right-hand side. So before I do any sort of dividing, there's something else I need to do. I'm going to grab some coffee. I want you guys to think about how to solve that equation for y prime. I think there's only 1 or 2 portions in the algebra classes leading up to Calc 1 that require you to solve equations like this. And it's when you study rational functions in both pre-calculus and in college algebra, we deal with some things like this. The trick is to get every term which has a y prime on one side and every term which doesn't have a y prime on the other side. So I'm going to distribute this, and that'll give me cos x plus y times 1 plus cos x plus y times y prime. All right, so I kind of take this cos x plus y and I distribute it over these two. And then on the right-hand side, I'll write this as 2y y prime cos x minus y squared sine x. And now I've kind of blown everything apart. I see that this term has a y prime and this term has a y prime. So I'll leave this term over here. I'll subtract this term over to this side. And since this guy doesn't have a y prime, I'm going to push him over there. So I'll get cos x plus y times y prime, that's this term which I'm leaving over here, minus this term, equals, I'll have my negative y squared sine x, and then this term that I'm subtracting over, minus cos of x plus y. So the trick is to expand everything apart, and then any term that has the piece you're trying to solve for, put that on one side, and any term that doesn't have the piece you're trying to solve for, you put that on the other side. So now every term over here has a y primed, and no term over here has a y primed. Since every term over here has a y prime, there's something special I can do.
You can factor out the y prime?
Yes. Factoring that out, I get cos of x plus y minus 2y cos x. And on the right-hand side, I still have my minus y squared sine x minus cos of x plus y. And now finally, I've got y prime times some chunk of slop equals some other chunk of slop. So I can divide over by this whole piece to get y prime on its own. So y prime will be all this stuff, negative y squared sine of x minus the cosine of x plus y, all divided by cosine of x plus y minus 2y times the cosine of x. And that, lads and ladies, is your answer. I do have one or two follow-up algebra questions for you. Can I cancel the cosine of x plus y's?
Yes.
No.
Yeah, so the answer here is no, I cannot cancel those because they're not common factors, right? We can only cancel common factors of the top and the bottom. So I know it's very tempting when we see things like that to cancel, but we cannot cancel them. Only if you could factor cos of x plus y out of the top and the bottom could you then cancel it. So a quick side note, don't write this down unless you really want to. Can't cancel cos of x plus y. Think of it this way, if I had something like 5 minus 3 over 3 minus 12, can I cancel the 3's? Well, 5 minus 3 is 2. 3 minus 12, what's that? That's negative 9. But if you canceled the 3's, you'd have 5 minus 1 over 1 minus 12. And those certainly aren't the same. That's 4 over 1 minus 12 is negative 10, right? Super duper not the same. This is negative 2/5. That's 2/9. So they're very different answers, right? So the question, can I cancel this, is something that you need to ask yourself very carefully. And the right way to answer that question to yourself, like on a test or in homework or anytime you're working with algebra, is can I factor it out? If you can factor it out from both the top and the bottom, then you can cancel. So my safety guideline here for canceling in fractions, we need safety guidelines just like OSHA. Safety guideline for canceling in fractions is factor first. If you can factor something out from the top and bottom, only then can you cancel it. And if you find yourself trying to cancel something, unless your immediate step before was factoring it out, just don't do it. I recognize it's tempting. I get that. That's why I ask. But let's be careful. Any questions about how we arrive at this?
Up near the top, derivative of y squared, that was a chain rule, right? 2y times y prime.
Yes, ma'am. Yep.
Okay, just wanted to check. Thank you.
So the 2y, that's the derivative of the outer function. And then multiplying by y prime, that's multiplying by the inner function. Yeah.
Yeah, thank you.
Of course. Other questions or comments on this one? Okay. Let's see if we can do something. So here they want y double prime. This is that same sort of business. Inverse trig functions. Yeah, so we started talking about this, but we didn't finish this, right? I think I did one of these for you guys. So let's do all of it. And then I would hope that there's something where we're going to differentiate with respect to some third parameter, but it doesn't look like they're hitting you with any of that stuff yet. And if they're not, I won't either. We'll just wait until the next section of the text. Okay, let's do it. Let's find the derivatives of our inverse trigonometric functions. They're listed here, and these will in effect be things you have to remember. What I'm about to do, you can think of as a derivation or a proof, but when it comes to using these things in problems, nobody wants to have to cook this up. So in practice, just like you have to remember the derivatives of the trig functions, you have to remember the derivatives of the inverse trig functions also. So think of this table, which is on page 214 in your textbook, as being something that you need to remember. People like the word memorize. I'm not crazy about the word memorize. Certainly it's something you need to remember. The best way to remember something like this is to solve lots and lots of problems involving it. Right? So if you look down here, there's plenty of problems involving inverse trig functions. I will give you some of them on this week's homework, but I won't be giving you all of these. If you're worried about not remembering the inverse trig functions and their derivatives, come back and solve more problems. The more problems you solve, the better you will remember them. But flashcards also work for some people. I don't judge. Whatever works for you is fine. But my advice is to solve as many problems as you can. So let's do this. I think I did the inverse tangent function for you guys last week. So let me kind of remind you how this goes. We'll do it with the inverse sine. So we want to find the derivative of the inverse sine function, the derivative of the inverse cosine function, the derivative of the inverse tangent function. Cosine, cosecant, cotangent, or just cosecant, cotangent. We can cook those up also, the secant as well. So let's start with this one. We're going to begin with the statement y is equal to the inverse sine of x. And then note that our goal is to find y prime, right? If y is the inverse sine of x, then y prime is the derivative of the inverse sine of x. Now you got to remember the definition of the inverse sine function. Y equals the inverse sine of x means, or is defined to say, the sine of y is equal to x, and negative pi over 2 is less than y is less than pi over 2. Less than or equal to, I should say. This part isn't super important for what we're about to do, but it is important to remember. This is the definition of the inverse sine function. It's got nothing to do with powers, nothing to do with reciprocals. The inverse sine function is not 1 over the sine of x. Absolutely not. Totally different thing, right? We mean inverse in the same way that the square root is the inverse of the squaring function, or that the logarithm is the inverse of e to the x. That's what we mean by inverse here. So we'll apply. We can differentiate this expression with respect to the variable x, then solve for y prime. Does that make sense? If y is the inverse sine of x, then the sine of y is equal to x. That's the definition, the inverse sine function. So this means the same thing as this. So if we differentiate through this and then solve for y primed, that will give us the derivative of the inverse sine function. The definitions of all 6 inverse trig functions and some very basic problems to kind of get you re-familiar with them if it's been a while since you did trigonometry can all be found in our modules. If you go to the review material, there's lots of stuff here on inverse trig functions and trig functions from Paul's online notes. Right here under trig review. Also, I guess it's all right there, yeah. Rational functions. Yeah, so if you need a review of inverse trig functions, come in here specifically to this bit. All right, this will kind of remind you what they're not. This is the most common mistake, is people thinking that these things have something to do with each other. They do not. Has the definitions here and then some very basic problems. Be good for you to look at if you forget this stuff. I'm not going to spend time on that in class. That's on you guys. You must know this shit. Right? If you do not know the definition of the inverse trig functions, you're dead in the water on these problems. So please make sure you remember them. From here, I'm going to apply ddx to both sides. All right, we're going to differentiate this expression with respect to x. So that means I'm going to have ddx of sine y equals ddx of x. The derivative ddx of x is 1. The derivative ddx of sine y is cos y times y primed. So I'm differentiating with respect to x, and I know that y is implicitly a function of x. So from here, I get that y primed is 1 over the cosine of y. That's okay, but it doesn't look like a good formula for the derivative of this function because it's full of y's. And I don't want y's, I want x's. So from here, what we want to do is figure out how can I write cos y in terms of x, knowing just that y is the inverse sine of x. Well, one option is to just plug this in. I could say that y prime is 1 over the cosine of the inverse sine of x. Right? I could plug in this y with sine inverse x. That's ugly though. So what's better than that is, again, using this definition. We say, okay, this means that sine of y is equal to x. And then using some Pythagorean identities. I'm going to use them very carefully. I'm going to square both sides. And don't worry, I wouldn't expect you to come up with this on your own. There's some real creativity here. And then use the Pythagorean identity, sine squared plus cos squared equals 1. Certainly that identity you should know, but the application of it here is not super obvious. So sine squared y plus cos squared y equals 1. What I have here is a cosine of y. So that's what I want to get out of this. This means cos squared y is equal to 1 minus sine squared y, which means cos of y is the square root of 1 minus sine squared y. So if sine squared, let me jump back a little bit. If sine squared is Well, I guess I could just do it like that. Let me say this then. Yeah, I guess we really, we'll do it like this. This is okay. Sine squared is x squared. And I could also solve this for sine squared, right? This means sine squared y is 1 minus cos squared y. So this piece is 1 minus cos squared y is equal to x squared. And now I can add the cosine over to both sides. So we're just playing around with Pythagorean identities. So this means 1 equals x squared plus cos squared y. We'll do it like this. And then subtract the x squared from both sides. 1 minus x squared equals cos squared y. And then take square roots. So the square root of 1 minus x squared is equal to cos of y. All right, so we get there either way. The upshot is the cosine of y here is the same as the square root of 1 minus x squared. So yeah, let's say it like that. I would say ignore all of this in the orange. There's another way to do this that I keep in my head. But all we're using here is this Pythagorean identity. Sine squared is 1 minus cos squared. That's always true because sine squared plus cos squared is 1. So I can replace this sine squared by 1 minus cos squared. And my goal is to solve for cos y because that's what I have here. So I've got 1 minus cos squared y equals x squared. I add the cos squared of y to both sides. That brings him over here. So I'll have x squared plus cos squared y. And on the left, I just have 1. Now I subtract the x squared over here. And then I take square roots. There's a couple different ways to do this. Now, we have y prime equals 1 over cos y. This must mean the same thing as y prime equals 1 over the square root of 1 minus x squared. And that's what we were after, i.e. the derivative d dx of the inverse sine of x is equal to 1 over the square root of 1 minus x squared, like this. And this is the second most important inverse trig derivative. The most important being the inverse tangent function that I showed you guys on Friday. I'll go through that one also. Just to be clear, I'm not expecting you guys to cook up this inverse trig function derivative on your own. I'm not expecting you to go through this process on your own. I am expecting you to remember this derivative. You must remember that the derivative of the inverse sine function is 1 over the square root of 1 minus x squared. It's a good thing to try and understand this because it's a great bit of practice with implicit differentiation. So I would be happy to take questions that you may have from this. So are there any questions on the derivation?
Sorry, I have a quick question.
Yeah, Robert.
Sin x squared equals x squared. Where do you get the squares?
I took this equation here,
Yep.
I squared both sides.
Oh, you just threw a square in there?
Yep, so here to here I square both sides. And then here to here, I use the fact that sine squared of anything is the same as 1 minus cos squared of that thing. That's the Pythagorean identity.
Okay.
And then from there, I'm just doing algebra. Okay, the creative step here is squaring both sides. Well, it's not obvious that to solve for cos y, you would at any point need to square both sides. But after you square both sides, you can replace sine squared by 1 minus cos squared. And then that will let you solve for cosine of y. Sort of that's what's going on. Your textbook might do this a little bit differently. We can take a look at the way your textbook does it. No, they don't even justify it. They just say like, here's what it is, right? Yeah, they just straight up say cos y is the square root of 1 minus sine squared y, which is true. It is the square root of 1 minus x squared. They're not wrong, but there's not a lot of explanation there. But same thing. All right, let's do the inverse tangent function next. So the first trig derivative you must remember, or first inverse trig derivative you must remember is this one. The derivative of the inverse sine of x is 1 over the square root of 1 minus x squared. Let's find the derivative of the inverse tangent function. Now, for those who are here on Friday, I think we did go through this then. We begin with y equals the inverse tangent of x, and that y equals inverse tangent of x is equivalent to saying the tangent of y is equal to x. And the associated domain restriction here is negative pi over 2 is strictly less than y is strictly less than pi over 2. And now we can differentiate on both sides. And the inverse, the derivative of the tangent function is secant squared. So when I differentiate on the left-hand side using the chain rule, I'll get secant squared of y for the derivative of the outer. And then I multiply by the derivative of the inner, that's y primed. On the right-hand side, the derivative of x again is just 1. And now I can solve for y primed. I get y primed is 1 over secant squared of y. And again, we have this identity. Tan squared of anything plus 1 is equal to the secant squared of that thing. This is the second Pythagorean identity. So secant squared of y is the same as tangent squared of y plus 1. And what is tangent squared of y? Well, that's x squared, because tangent of y is x. So this is 1 over x squared plus 1, because the tangent of y is x. So this tan squared y is x squared. This one is this one, i.e., and here's the second inverse trig derivative that you must remember forever and ever, amen. Don't let this catch you out. There are a lot of tricky problems that require this as a starting point. All right, so you got to know your inverse trig derivatives. The two most important by far are arctan, right? This one, inverse tangent, and arcsine, the one we just did. By far the two most common inverse trig derivatives. So you must remember these. The derivation here isn't so spooky. But again, you're not responsible for the derivation. You are responsible for the result. Questions on this argument? Okay. We can do one more. Let's see. Maybe we should do some examples. I could just tell you what the other ones are. Yeah, so let's say you guys probably aren't getting too much out of these derivations since you're not responsible for them. Nobody's gonna beat them into their own head. So let me just come over here and we'll solve some problems with them instead. Yes, of course. All right, so first let's write these down. At least the ones you're gonna use a lot. So the derivatives of inverse trig functions. These things you must remember. The derivative of the inverse sine of x is 1 over the square root of 1 minus x squared. The derivative of the inverse cosine of x. This is easy. It's just the negative of the derivative of the inverse sine of x. And that pattern holds in general here. The derivative of the inverse tangent of x is 1 over 1 plus x squared, or you can write it as 1 over x squared plus 1, whichever order you want downstairs is fine. The derivative of the inverse cotangent function is the negative of that. And the derivative of the inverse secant function is 1 over x times the square root of x squared minus 1. Really, this x should be in absolute values, but we won't worry too much about that. And the derivative of the inverse cosecant function is the negative of this. All right, so these are your 6 inverse trig functions and their derivatives. Now, we do have to know these. The pattern is nice, right? Every function and its cofunction are the same derivative, just with a negative for the cofunction. So if you remember sine, tangent, and secant, you get cosine, cotangent, and cosecant for free. So my advice here is to memorize this. This. And this. And then you just remember those 3 along with the rule that if you have a cofunction, its derivative will just be the negative of the normal one. Okay, let's solve a problem or two, and then I will let you guys go. Some fun involving some inverse trig. Yeah, something like these over here seem like fun. We can take a look at I guess you've got the odd answers in the back. So maybe I'll do 50 and 52, and I'll let you guys think about 49 and 51 if you want to try those for challenge problems. They'll be available to you. There's on the back of the book there. So let's start with the inverse tangent of x squared. All right. I would say recall that the derivative of regular old arctan x is 1 over 1 plus x squared, like this. So I'll need this fact together with what rule to get the derivative of this function? See, it's in chat here. Let's see. Yeah, good. The chain rule, right? Here, my inner function is x squared instead of just x. So I need to use the chain rule when I differentiate this. So the derivative, y prime here is the derivative of the inverse tangent of x squared. If I differentiate the outer function, leaving the inner function alone, the derivative of the inverse tangent function is 1 over 1 plus its inside, which in this case is x squared, left alone, squared. And then we multiply by the derivative of the inside. So we're just practicing the chain rule here, but we have a new formula. The derivative of the outer function, the derivative of the arctan thing here, this is a new thing. And now we can clean it up. 1 plus x squared squared is x to the 4 times the derivative of x squared is 2x. So this is 2x over 1 plus x to the 4. Oh, good Lord. My dog just farted and it's awful. All right. Questions on this one? If not, let's look at a couple others. Let's look at, we said we would do 52 also, right? The inverse cosine of the square root of x. Same thing. It's inverse cosine, right? Yeah. So they're writing it as arc cos. That's the same thing as cosine inverse like this. I prefer the inverse notation. Here, the little thing that we need to recall, the new derivative formula that we have is the derivative of old-fashioned inverse cosine, which is the negative of the derivative of inverse sine. So this is the negative of 1 over the square root of 1 minus x squared. Only now, instead of having an x inside, I have a square root of x inside. So here, y primed is going to be d dx of the inverse cosine of the square root of x, which is going to be negative 1 over the square root of 1 minus the square root of x squared. And then by the chain rule, I have to multiply by the derivative of the square root of x. So here there's quite a bit to do to clean things up. First, the square root of x squared down in here, when I take this guy and raise it to the power 2, the little square root inside goes away. So I'll get negative 1 over the square root of 1 minus x. And now I'm multiplying by the derivative of the square root of x. That's the derivative of x to the 1/2. And to finish the job, I need to find the derivative here. So this is negative 1 over the square root of 1 minus x times 1/2 x to the negative 1/2. And you can leave it like this, that's fine. If you want to clean it up, you can. Kind of extra cleanup step here looks like this. This is 1/2√x. Like that. You could combine them into a single fraction if you wanted, but you don't need to. Questions on these last two examples where we're using the chain rule together with some inverse trig stuff? Okay. I would like to do one more problem. We started a little bit late today, and then I'll let you guys go. Something a little bit scary looking, but not something totally outrageous. Let's take a closer look here at number well, these are all chain rule things. I'd like to do something that's more than just the chain rule. Let's look at number 57. Let's find y prime and the expression x times inverse sine of x plus the square root of 1 minus x squared. So this will be our last example for today. As someone who does a lot of Calc 2, this is a fun problem because it's kind of foreshadowing something that you'll be learning later. This is a little bit of foreshadowing for something called integration by parts. But for us, it's just a good differentiation problem. Let's try to find the derivative. So here I know y primed will be the derivative of x sine inverse x plus the square root of 1 minus x squared. And this piece requires a specific rule. This piece requires a specific rule. What's the specific rule required for the first piece?
Product?
Good, yeah, the product rule. So here I'll have the derivative of x, which is 1 times sine inverse x left alone, plus x times the derivative of sine inverse of x, which is 1 over the square root of 1 minus x squared. That's my product rule for this piece. And then I have to add that to what I get when I differentiate this. What rule do I need for this?
Chain.
Yeah, this is a chain rule thing. This is the derivative of 1 minus x squared, all raised to the 1/2 power. So when we differentiate that, we'll get 1/2 times 1 minus x squared to the 1/2 minus 1, which is negative 1/2 power, times the derivative of the inside. Well, the derivative of 1 minus x squared is negative 2x. So to go over here, we're using the chain rule. And to go down here, we're using the product rule. Now let's see what we get from all of this. Here, 1 times the inverse sine of x is just the inverse sine of x. And then we have plus Here I have x over the square root of 1 minus x squared. I multiply those two. And then over here, the 1/2 and the -2 are going to cancel. And I'll write it like this, 1 minus x squared to the -1/2 times -x. And then if you think about this, this is sine inverse of x plus x over the square root of 1 minus x squared. And now this negative here is going to make this whole term negative, so I'll have minus. This piece is 1 over the square root of x minus 1 squared, or sorry, 1 minus x squared. And this is an x. So these things go away, and you just get the inverse sine of x. So this is neat. The derivative of this somewhat complicated looking thing is the inverse sine of x. In other words, well, we'll talk about it later. This is something to do with what's called an antiderivative. But this makes for a good problem because we've got some product rule here, some chain rule here, and then the second piece from the product rule interacts with the piece from the chain rule. They actually add up to 0, so you end up just getting that first piece. All right, I will go ahead and conclude here. I think I saw this morning that last Friday's lecture hasn't been uploaded yet. I'll make sure to get that up today along with today's lecture. I hope you guys have a wonderful afternoon. Please watch, I will be opening up a new homework today. It'll take me just a few minutes to get that nailed down after my next class. And then I do have an office hour today from 1 to 2 p.m. Your exam ones, those will all be graded by Wednesday. That is the goal. It might be ready by class time. It might take a little bit later, but definitely by Wednesday, no later than that. Any burning questions for me before we sign out for the day? Alrighty, I hope you guys have a lovely afternoon. Come by office hours if you want to talk problems. Otherwise, I will see everybody on Wednesday.